In this video, we will explore signal reconstruction from samples. The goal of reconstruction is to go from a discrete time signal to a continuous time signal, basically the opposite of sampling. As mentioned in the videos about sampling, we want to choose the smoothest signal that goes through a set of samples. This, of course, is not so easy to implement. There are many possible techniques to achieve this, but they all center around the same concept, which we will present here. Let's suppose that we start out with a set of samples and we want to reconstruct the smoothest signal that goes through these. Now we can kind of see that perhaps this dashed line is the smoothest such signal. However, as opposed to what we have seen before in the sampling videos, we can't simply plug in a value of t times f sub s into a closed form equation, because most often there is no closed form equation. All we have is a bunch of samples, not an equation for them. So how do we reconstruct a continuous time signal that is the smoothest from a given set of samples? Well, there are many possible approaches. For example, what we can do, let's redraw the same sample pattern. We can place a box or a steady level at each one of the samples until the next one. So something like this. We place a box around this sample at its amplitude. We place another box at the amplitude of this one until halfway to the next sample. Then a box like this and a box like that, and so on. And our reconstructed continuous time signal then is going to be this signal highlighted in blue. It's a discontinuous signal, but it remains steady at the sample values. You can imagine that if these samples were really close together, this would almost look like a continuous kind of a signal. It would be pretty smooth. This is the easiest possible way to reconstruct a continuous time signal. Now notice the fundamental difference between the samples and this blue signal is that the blue signal is defined for all points in time. Therefore, it is a continuous time signal. Let's look at another possibility. Again, we're going to look at the same set of samples, but this time we're going to place a triangle at the amplitude of each of the samples, extending from the previous sample's base to the next ones. And what we're going to do is we are going to add up all of the contributions from each one of these triangles in between the samples. In that way we are interpolating values in between samples, and again creating a continuous signal. What this will create is actually a linear interpolation where we are essentially connecting the dots. That's all we're doing. Now again, this may be smooth or not. It has these corners, of course, so it's not the smoothest possible version of a signal through the samples, but it's smoother than the box one. And again, if these samples are close together, this will be a quite smooth representation. Now this one here was the easiest one to implement. This one is a little more complicated. It requires adding up these contributions in between samples, performing this interpolation. And further, we can imagine a lot of different possible shapes that we can place at the samples in order to perform reconstruction. Each one of these is generally referred to as a pulse. And so we have different kinds of pulse shapes. We'll call them mathematically P of t, and they may be a box, which is what we saw over here. They could be a triangle, as we saw over here. They could be parabolic. And there are many other ones that get closer and closer to the true smoothest possible version of the signal, but each one gets more and more computationally intensive. And therefore it may or may not be advantageous to actually use more complicated pulses. So for example, the samples are really close together, and this is the easiest possible implementation of reconstruction. Why not use it if it's going to give you an acceptable result? The general form of the equation then for reconstruction is going to be that xr of t, so we're going back to our reconstructed signal, is going to be an infinite summation of these pulses. Because all we're doing is just adding up all of these pulses. Each one of these happens to be 0 outside of a certain range, and so therefore doesn't contribute anything, but in between two samples we add up all the contributions. So we go for all of our possible samples at each n. We take a pulse which has an amplitude of 1, and we shift it to be centered around the sample that we're analyzing and give it the amplitude of the sample. This is exactly what we did right here. We took a triangle with an amplitude of 1, we centered it around this sample, and we gave it its amplitude. Same thing over here, same thing over here, same thing over here, and then we added up all of these contributions, everything that we have here, and that's how we get our continuous time signal. Now, one thing to notice here is that I have a t sub r. This t sub r is going to determine the spacing in between the samples when we perform reconstruction. Now, t sub r in reality is arbitrary. It is not necessarily equal to t sub s, even though that is what would usually make sense. So specifically, let's say that we have a continuous time signal that we sample, and this is at some sample rate corresponding to a sampling period of t sub s. And now, after we do this, all we have left are sample numbers. Sample number 1, 2, 3, 4, and so on. We don't really know anything about the time in between these samples unless we also know the sample rate. If all we have is a series of samples, all we know is their sample number. So therefore, the spacing between them is technically arbitrary. So when we perform reconstruction, and we again look at the time domain, this time we're starting off at our samples, and I can place them when I reconstruct arbitrarily close or far apart. So let's say that I actually place them closer than what I had originally over here. So now this is the same exact set of samples as I have right here, still sample number 1, 2, 3, 4, but I chose a much smaller t sub r, a much smaller reconstruction period. And therefore, the reconstructed signal through here is going to be different than the other one, than the one that we started with. In fact, it's going to be shorter in duration because my samples are closer together, and also higher in frequency because things are going to vary more quickly in this one. And vice versa, if I choose to place the samples further apart, the frequency will decrease and the time duration will increase. Altogether, we have seen how to perform reconstruction, that is, going from a discrete time to a continuous time signal. We have also seen that the reconstruction rate is arbitrary, but is usually chosen to be the same as the sampling rate for consistency.